I think let's continue. I think we touched upon this already. So there are three major file annotation formats. Pascal VOC, its historical significance because I think this was the first format, but then later it evolved into Cocoa. Cocoa became more widely used than the Pascal VOC, but then all the latest modern object detection, which was based on YOLO framework, uses YOLO format. So they use different file types. The Pascal VOC uses an XML files. It stores the bounding boxes in x1, y1, x2, y2 style. Cocoa uses a JSON instead of an XML file. Then it stores the images, annotations, and the categories. And then the auto format, what it does is if it basically creates one text file per image. If you have 100 images, then it creates 100 text files, and each text files contains the number of objects labeled in that particular image. So in the example that we demoed before the break, we labeled 4 objects, 3 cars, and 1 person. And if you open that text file, it contains 4 labels, and each row is of the format class CXCYWH, and they are normalized coordinates between 0 and 1. Some of the good annotation practice is that you start with a problem statement. You know what is the use case that you are trying to solve, and you know what are the target objects that you are trying to identify. So you need to, just like how I created a project and I defined 3 classes like the car, bus, and the person. You need to define those class names. And then it's also good to identify the edge cases before labeling. What are some of the edge cases could be is that there are uh, 2 classes, they are visually similar, and what kind of class confusions can happen, what kind of inconsistencies can happen, could also be considered. And then write down some annotation guidelines before you start the labeling process. When you're doing a sort of an academic project, right, you do it at a sort of an POC level, and probably you have a very relatively small data set with relatively less critical classes, and probably you're not like in pay much attention to the edge cases. But if when you are developing a real world industrial use cases where you are deploying these models at very high stake environments such as medical diagnosis, or let's say aircraft engine inspections or food quality inspections, they are at very high stake environments, and we are building a system to automate these inspections with high accuracy and high reliability. And a lot of the object detection's performance issues are attributed to the labeling quality. If you see, if we these kinds of images, different kinds of each basket is really which one takes the maximum space? Okay. I have not quantified that, but they are not that big. Mhm. Where to use what? So it depends on the model that you have selected, whether they have been pre-trained on what format. There are older models that is being trained on Pascal VOC format. There are some intermediate model architectures like such as faster RCN and mask RCN that might have been trained on Cocoa format. But the modern things mostly they are trained using YOLO format. That is the main criteria. YOLO. See, you can use one format and you can also convert those from YOLO format to Pascal VOC in case if it is required. Yeah, that we do typically in our projects. Yeah, so this is one of the data leakage things that we need to take care. So if your data contains a lot of videos and you will be labeling those objects throughout the video. And let's say you have some 1,000 videos. One way is that let's say each has some sort of 100 frames, like right, 1,000 into some 10,000 or 1 lakh images you have labeled. All comes from 1,000 videos. But if you do a normal stratified split, um, the train validation and split will have equal representation of all those 1,000 videos, right? Which means that that is not the recommended practice. So what you have to do it is that you keep those video split isolated, that you don't have the same video represented in both in train and test. Okay. Yeah. Normally you don't do, but if you're constrained by data sizes, then you put all videos into one and then divide them. But if you have like thousands and thousands of videos, then you could actually divide them by videos and don't have the same video represented in both train and test. Then that would actually lead to data leakage. And someone, if they are auditing your model and if they came to know that you are doing it one, probably they will challenge you. So they say that I don't believe your metrics anymore because you have leaked your data and you might have good accuracy, but I don't agree with that.
Face recognition example, say in a video, if somebody is trying to recognize a specific face,
Yeah.
in that case, there's a CCTV footage. Cases that they are trying to recognize one specific face. So in that they will have.
Yes. Yeah, because then we need to have the same person represented in both train and test.
Another question. So when we go back to the page where you annotated, right? The third car that we selected was behind the
Yeah.
second car. So that overlapping coordinates, how does that work? Because the third car's, coordinates were behind car two, right? So how does that work, when we select the coordinates of that car?
So when we're labeling, we just have labeled it like this, right? That's that. Yeah. So here we have some occlusion, that some portion of this red car has been occluded by the silver car and the yellow car.
Right.
But the occlusion percentage is not too big. Still majority, almost let's say 70-80% of the car features are still available. I think the battery is dry. No power. So so here if you see, there is 70 to 80% of the car feature is still visible. So the model would be able to cope up with it. But in case let's say this car, right? There is one which has some sort of an above. Identifying that car will become a difficult. But for human, I would say there is a car there. But for model to identify that a car, it will be very difficult. Okay. Then what you do, so that's where the labeling problem also comes. So the labelers, that's what we are speaking in the break also. We sometimes outsource those to some third-party companies. The data scientists might not be labeling them, right? We just give them to some, because the manual tedious jobs and it has to be done at a very large scale, then we outsource them. So those people, they know that this is a car, so they might go and draw a bounding box here. Okay. So let's say the model will not be able to identify that, then that be impact your evaluation criteria. So your accuracy will come down. Typically, we should advise them do not label this unless you see at least 50% of the car.
How do we like verify or validate that labeling is that right before we train?
Through manual review process. So you should have a QA process for labeling. So there will be like thousands of labelers will be labeling your millions of images. Depends on your scale of the project. And then there will be like low level labelers, and then there will be some supervisors, then there will be some managers, and the supervisor has to go through a review process. So probably they will review randomly a 30 or 40% of the images that has been labeled by the labelers. So if there is any quality issues, then they send it back. They will accept or reject. So first they will label it. It goes through the reviewer. There will be 100 labelers will be there. There will be like 25 reviewers will be there. And then the reviewer will be reviewing all the images. He will either accept or reject. So there's a proper intense QA processes involved in this. It's almost like running a factory. You could do, but depends on how reliable that agents are. If we have a reliable agent that can do, sometimes what happens in terms of automation, we make things worse. So, and ending up spending millions, and then you realize that you made it worse. And then instead of that, I would have put some 100 more labelers and probably improved it. So you have to make some informed decision whether. Yeah, we could do some kind of automation. That's why we say it's not. It couldn't be done in a fully automated way. We could do some sort of a semi-automation in it.
Capture images to be there. We
Yeah.
will ask us to select
Yeah.
space, cars, traffic light. Is that available anywhere? Like,
Yeah. So basically, they are collecting data. So they are using your intelligence to you are able to identify where the car is, but the computer cannot do. So now they will use this data to retrain it. Same thing happens in ChatGPT also.
that's using us as labelers.
Labelers. This is one smart way of labeling. It's called labeling. Yeah, crowdsourcing. Hmm. In YouTube, that's not particularly object detection, but in video object detections, we do have timelines that we say that, hey, there is a car starting from second minute to always up to 2 minute 30 seconds. You could also have a timeline. Yes, video analysis. Yes.
Maybe you see that.
Yeah.
So video one.
Same. Instead of importing images, you import videos. Yeah, there is a little bit of motion detections built in this trackers. So they can track the movement of the objects along the frames, and they can automatically label those. If you label one frame, all the subsequent frames can be automatically labeled. As long as the movement is small and the movement is linear, this tracker works well. But if the movement is very sudden or it can be very zigzag, then the accuracy is not reliable. Uh, yeah, you could explore this tool. There's like a lot of automated features. So this is what we use for bounding box. There is also for segmentation, which we will look next week, right? We might use, let's say, a polygon, something like this, where it will create a mask instead of a bounding box. This is even more tedious actually. Segmentation, yeah. Each car exact boundary it will detect. So here it's a very coarse boundary, but for segmentation, it will give you the exact boundary of this. Okay. Where am I? Okay, here.
Sir, one question on this one.
Okay, so the next important concept is called intersection over union. So we say the object detection model is going to predict bounding boxes. Okay, so that's basically the task that has been assigned to that model. And the model is going to predict your bounding boxes. But now, how do we tell this bounding boxes is good enough? How do we evaluate the goodness of these bounding boxes, right? So for that, we have a mathematical way to evaluate this. That's just called intersection over union, which means given a reference bounding box, or they also called as ground truth bounding boxes, we then have a way to compare the predicted bounding box by the model with this reference ground truth bounding boxes. It's basically the ratio of the area of the intersection, the common or the overlapping region between those two bounding boxes over the total area or the union of those two bounding boxes. So it's also pretty similar. So the intersection or the overlapping region is basically this dashed region. So what we take is this area is calculated over the total area. So this ratio is basically, it's called intersection over union, and it ranges from the value of 0 to 100 or 0 to 1. Okay. 0 means there is no overlap at all. 100 means they are perfectly overlapping on top of each other. Okay. This gives an indication of how good the predicted bounding box is. Okay. Normally, you don't get a perfectly overlapping bounding boxes. So if it overlaps 50% and above, it is considered to be a good bounding box prediction. Okay. This 50 is what is a typical recommended value to check whether that bounding box is good or not. But sometimes it can be more, or sometimes it can also be less. Okay. So there is the IOU is used to determine whether the in order to evaluate any machine learning model or deep learning model, we calculate accuracy. And in order to calculate accuracy of a machine learning model, what do we need? We need the true positives, the false positives, and the false negatives and the true negatives, right? So the accuracy is mostly is TP, true positives plus true negatives divided by the entire data. So how do we determine whether a model's prediction in machine learning world has a true positive? Hello. Let's say if it is a binary classification model, whether it is email is a spam or not. You have some 100 emails, you're trying to support vector machine or something like that. And then the model outputs whether the email is spam or not. So now what you do, you know whether that email is spam or not, you know the ground truth. Then you get the model predictions. The model will say it's a spam or not. If they match, then it's a true positive. If it not matching, then it becomes a false negative or false positives, right? But that is a very simple comparison. How do you determine a true positive in object detection? Yeah, so
in the image, if we are trying to detect, let's say the face is 100%, the body might not be 100%. So if the face is there, then that means it's true. That's where what we did.
uh, so here the model output bounding boxes, like how the email classifier outputs whether it is a spam or not. Here the model outputs a list of bounding boxes. And
We have the coordinates.
yeah,
That is a
reference.
reference targeting that is a
Ground.
Y. And now after training the model, how model defines the coordinates,
Yeah,
we'll compare them Y and Y hat.
yeah.
So we'll check if this
How you will compare Y and Y hat?
distance
is
zero.
That is what is intersection over union. You now are able to map it, right? If I want to compare two bounding boxes, we need some sort of a distance matrix, whether they are close enough or not. That distance matrix is nothing but the intersection over union. Okay, so what we say is, okay, you have your ground truth bounding box and you have your predicted bounding box. You calculate your intersection over union. If this intersection over union is more than 50%, then that becomes a true positive. Okay, if not, then that box becomes either a false negative or a false positive. Okay, so the ground truth becomes false negative, the predicted becomes false positive. Okay. Okay. Then non-bounding box. So you're saying this denominator is not needed? So if we have one bounding box, this is, let's say, ground truth, and this is my predicted. Okay, in this case, the intersection is 0. So 0 by anything is 0. So my IOI will become 0. So if I, yeah, so in this case, it has about some 20%, 30% overlap is there. Right. So if you calculate it, IOI will come 30%, something like that.
That means image is not matching. So if it is 0, then it is not.
This will become let's say this is one, right? Then this will become a false positive. Let's say this IOU is less than 0.5, right? Then this is a false positive.
Yeah. This question shows that this image. So if we see that there is only one cat which is there, so that can come in one bounding box. Balance is already grayed out or faded or non-pixelated.
This is actually ground truth. So the model is not outputting two boxes. The model is outputting this yellow box. So this is Y. In your machine learning world, this is Y, and this is Y dash. Now I want to compare an Y and Y dash.
It is able to identify predicted image. That means the value of IOC will be slightly higher, close to 1.
Yeah. It's a very key metrics in object detection. So this helps to determine whether a predicted prediction of the model can be classified as a true positive or false positive or false negative. Only if we know the true positives, false positives, and false negative, you can get a model accuracy. It can be of any size. There is depends on the model performance, right? But initially, it could just draw some random boxes like this also. Slowly, it will improve. Then finally, if you see, it will draw some better bounding boxes than it was in the previous. Maybe still it is not good. If you train furthermore, then slowly this box will start overlapping here.
Let's say model predicted a smaller box. We can.
Oh, okay. So you're saying it is like this. Then IOU is like uh, yeah. It will never be more than one, but it's yeah, something like that, 0.8. See here, although it is within the box, it is not covering the full object. So it doesn't mean that it's a perfect prediction. Okay, see, let's say I have a box like this. So in this case, the yellow has a better IOU than this red box, although this red box is within the ground truth box, because this box is useless for me.
Say this box, let's assume that it's 10 by 10 box. How do we standard the boxes should be more than more about the same temperature, then we will start doing that.
No. There is nothing like that, but it can try to predict any aspect ratio, any size of the bounding box. There are ways to eliminate or filter out unwanted bounding box. And finally, there will be one final set of bounding boxes. In that final set of bounding box, we will calculate this intersection over union, comparing the ground truth and the predicted box, and then come up with the true positive, false positives, and all those things. There is no any predefined rules that the box has to be of a certain size or box has to be of a certain aspect ratio, nothing like that. There is a concept called anchor boxes, which will be touch upon it. Basically, they are predefined aspect ratios and different sizes, which the model takes in as a cue or sort of an anchor in order to identify different size objects and different shape of an objects.
Let's say in the medical field, generally the sizes are pretty standard and defined. Right? So, or let's say any image. So it will be standard in this. And generally, if you have to look at a particular object, generally the sizes would be certain range. Let's say
Yeah.
500, that would be better, but say cubic or something like that. Give me an example. So, like, if we can avoid that initial
Yeah.
kind of 1 by 1, 2 by 2.
Yeah, that also is possible. So I kind of follow you where you're going. If we already know the domain,
Correct.
right? We already know that the object is of certain range. This will be from this minimum size to this maximum size, right? Then we can put some post processing to avoid some false positives. You know for sure my object will not be less than 100 pixels. All those tiny 2 pixels and all will definitely be false positives. Then you can just filter it out.
Might take a lot of turns to independent force.
Okay, yeah. During computation, there is no any way to add this heuristics to limit the model to detect only of certain size, but you can do it all this in mostly in post processing.
Just that to start after certain size.
Okay.
Like for example, let's start with 5 okay. Deviation. Start from that. Ignore all the previous ones.
That is where we have this concept called anchor boxes. Not sure whether it is included. Yeah, I'm not included it. Probably I removed that in previous things I did. So there is concept called anchor boxes. This is where we know that, hey, in the real world, the objects is of certain size and certain aspect ratios. There are some tall objects, there are some wider objects, and there are of different sizes, right? And there is no any very tiny objects. So the model will not be trying to detect those unwanted objects.
The timing object, they might be enlarging unnecessary. For example, I have it could be 2 by 2 kind of let's say 2 by 2 window. So box will have to go and identify, let's say, I know different kind of stuff, let's say some sort of scan which we have done, let's say Excel or 3D scans. So if you identify very smaller, minute defects, something like that. So probably there is no point going beyond certain.
Yeah.
Which,
Yeah, exactly.
that's what it is.
Yeah.
Either
Yeah. Okay. So we looked at intersection over union. Then there is one more important concept in object detection is called non-max suppression. Okay. This non-max suppression is a post-processing technique. Okay. So as I told you, the model cannot directly give you the final list of objects in one go, because it is not that powerful to tell you in one go, just give me the final list of objects. It can just make guesses, right? Because it's just trying to scan the image, and then it is trying to find the features, and it is trying to correlate that features, and then it's trying to, based on those learned spatial intelligence, it is trying to guess, hey, there is a probability of an object present in this bounding box. It is just giving a probability estimation. Okay, so that probability, first what you do, you get as much as probable object detection from the model. So that's why it will give you thousands and thousands of probable detections. Then from that, you try to filter out which is relevant, which is important, which is correct, using certain post-processing techniques. Okay. And one of the important post-processing technique is called non-max suppression. Okay. This is a way to remove the duplicate bounding box predictions. The model does not have the capability to give just one single bounding box per object. It will give you multiple bounding boxes per object. So you need to select one bounding box from that multiple predictions of that model. Okay, but how will we select it? That is why we have this non-max suppression. It works on a greedy non-max suppression algorithm. So suppose, for example, this is a cat, right? So now what we have 1, 2, 3, 4, 5 bounding boxes out there, but out of which probably there is only one is correct. Now, how do we do that? First, we remove the boxes with, let's say, very low threshold. Okay, we said that we will keep the bounding box only above 50% confidence score. In that case, we can remove one which 0.3 and 0.4. Then we are left with the 3 bounding boxes. We create, the model predicts. Yeah. What we create is the labels. When we create labels, we do only one box per object.
Model is created.
Yeah. So the model doesn't know where this boxes is. It is just trying to predict, oh, probably there is a cat here, probably there's a cat here, probably it kind of in a close proximity, it will draw multiple 4, 5, 6 boxes. Out of the 4, 5, 6, maybe one is only correct. But it doesn't have the capability to give just one box per. So that's why we are following this technique to remove those duplicates. So there are like 5 steps. First, we can directly remove the boxes which are less than a certain value. What is our 0.5 is our limit. Anything 0.3, 0.4, we directly eliminate. Then remaining we have 0.7, 0.8, 0.9, out of which we can order them like from low to high. Then we can keep only the high confidence. But suppose you might have 3 boxes exactly with 0.9. Okay, then out of this 3 boxes exactly with 0.9, which one you will select? Then you will select, have to calculate IOU among all these 3. Okay, so then you calculate intersection over union between the ground of among all these 3. Okay, then you remove them by, if there is if 2 boxes are overlapping each other more than, let's say, 50%. Okay, and they are exactly the same, then you can just drop one of them. You can drop any of them, it wouldn't matter. Then likewise, if you do is, you will end up with just 1 boxes per object. Still, then there will be duplicate boxes which cannot be filtered through these mechanisms, and that is where your model performance will go down, because only one boxes can be taken as a correct prediction for one ground truth, right? If there are very highly overlapping, or probably not highly overlapping, one is sort of on the lower left 50%, another is on the right 50%. They are not actually overlapping, but out of these 2, which one you have to only probably take one as a correct prediction for the ground truth. The other one will automatically become an incorrect one. So that will increase your incorrect predictions and your model performance will come down. Okay, these types of things can also happen.
Yes. Things which is down.
Okay.
It will have multiple components. So in that case, you remove it and then you
So in this, for this red t-shirt person, we have 2 red boxes, no? So, but in this, it's a very simple case. We select one with the highest confidence score.
So, but when it is predicting, it will predict all 3 as first, right? It will have
Yes.
3 objects.
Yes.
So each
See,
object will have its own bounding boxes.
yes.
Prediction.
Yeah. See, this is correct. Because there is no any overlapping boxes. In for the blue one is also correct. There is a problem only for this guy, because it has, the model has predicted 2 boxes. It's very simple. I'll just keep the one with the 0.9. I'll just remove this 0.6. I think that's what it will do. So I'll remove the 0.61. Likewise, I will remove it. Okay. And some modern directions. See, this NMS is one of the key concept, but it is also one of the area where there is a lot of error happening, because we cannot accurately filter out one. Sometimes in that process we eliminate the correct ones and keep the wrong ones, right? So it's all just heuristics and some sort of, and yeah, this is not very physics based methods, right? There is no any physics or any real science involved in it. This is all just some sort of an logic and some analytics. Sometimes it works, sometimes it doesn't work. So that's why, although it's very powerful, a lot of models is based on this. Later, the researchers found that this is one of the key area where there is a lot of mistakes are happening. Then they came up with a method, how can we totally eliminate this? So instead of doing post-processing, they trained the model to give only one box at the final predictions. So they integrated this filtering within the model training itself. Okay. So the modern, you will, once you get into this field and when you start implementing it, when you go a little deeper and when you do a little bit of reading, you can see a lot of blogs. There are models with NMS. Then recent, there are more NMS free models. Okay. Which means the NMS free models has two advantages. One, it is faster because you don't have to do post processing. The post processing adds extra latency. The NMS also introduce a little bit of error. Okay. But you have to compare and see which works best. Sometimes the post processing NMS process can be accurate than doing prediction in one go. Okay, so it's all a little bit practical. You have to experiment and then see. But I'm just telling for learning purpose. The latest modern YOLO frameworks, they also have NMS free options. Okay. So this is very, very important area because we need to understand how the object direction evaluation happens. Okay. We touched upon it when we discussing about the intersection over union, but now let us pay attention carefully and understand these concepts. So in order to evaluate any machine learning model, we need to determine the true positives, false positives, and false negatives. In your object detection world, a true positive is the prediction where the intersection over union of the predicted bounding box and the ground truth bounding box is greater than or equal to a preset threshold. And typically that threshold is 50% and above. And it also has to have the class name correct. It not only has to predict the bounding box correctly, but it also has to predict the classes correctly. Okay. So in the previous example, the cat box overlaps with the cat ground truth box with an IOU of 0.72. I just make up some number. It's not mathematically correct. But then what happens is, let's say, so when does false positive cases come? So we understood true positive cases, right? So when does false positive cases? This is where the lot of confusion will happen. Now, if the IOU is not above the threshold, then that predicted box, right, it becomes a false positive. But it can also become false positives if the class name is not correct. Okay. So dog predicted as cat, or if the IOU is less than a threshold, then it becomes a false positives. Now we also have false negatives. Okay. So now if you have, if we have like an image, let's say let's say if you have an image like this, and then you have three objects, let's say like one apple, something like that, and then let's say one car, and then let's say there is one tree, something like that. Sorry. Okay, so then let's say we have the green is the ground truth. And then let's say yellow is the prediction. Now we have one prediction like this. Let's say we have. Okay. Now we calculated the IOU here, for example, is 0.7. And this is 0.8. And this is 0.3. So here it predicted as apple. But here it predicted as bus. And here it predicted as tree. Okay. And there is also some more bounding boxes here. And then there is also like, say, one more apple, something like this. Okay. Now you tell me which ones are the true positives, which ones are the false positives, and which ones are the false negatives. This one? Why? Okay. So the IOU is more than 0.5 and the class name is also matching. And in this case,
False negative. False positive. False positive.
okay. So this box is false positive. Why? Because yeah, although the IOU is matching, the class names is not aligned, right? Oh, okay, because it's a car, but it predicted it's a bus. Right? So in this case, this one, this is actually 0.3. This one?
It is 3 and
False negative.
This is tree predicted as tree. Sorry, anyone? Yeah. So this is false positive because although the class name matches, the IOU is less than 0.5. No. So that's why it's false positive. Okay. This one. Sorry, false negative.
True negative.
No.
True negative. That's only classic.
There is no ground truth. So it's actually a false positive. No. It just made some false predictions there. The yellow one is model predictions. The red ones are the ground truth. There is no any, there is no object there. The model wrongly predicted there is an object there. So it's a false positive. This one? 0. It may have predicted that this is an apple, but my IOE is 0 because there is no object itself there. So it's a false positive. This yellow box? Yeah. No, false positive. It's the same like this box. So it is the IOU 0. It might have predicted it like a car or something. But
False negative.
yeah, I mean that. We have one more, right?
False negative.
Yeah.
True negative.
So he's already ahead of us. So he already predicted that this is false negative.
Prediction or
Yes, that's why it's false negative. False negative means the model missed to predict that object. There is an object, but the model told there is no object there. There is no true negative in object detection. All these ground truth pixels are true negative. Sorry. What happened? Oh my God, I missed everything. Okay. So, but you understood, right?
They've not predicted anything. Because you don't know even that exists. It doesn't. There can be multiple things.
So,
if it identifies.
sorry, where is the doubt in this apple where there was no prediction? It's actually a false negative because there is actually an object there, but the model said there is no object. which means it says that it is a negative. There is no object. No object means negative prediction. So it's those negative prediction is actually a false negative prediction. No, yeah, it doesn't have anything to. No, it has something to predict, but it missed it to predict. Understood? See, it's an actually there's an apple there. The model's job is to predict there is an apple and draw a bounding box there, but the model completely missed it. So which means you need to account this as a false negative. Actually, there is an object you didn't detect it. So I'm going to penalize you that you missed this object. So the false negatives are the ones which the model completely misses.
Can we say like this? If it is able to identify some intersection score, that becomes some sort of positive. If it is
Yes.
class name is correct, it becomes true. If it is not, then it becomes false positive.
Yes.
If in case it is failing to capture any intersection score, that becomes
positive.
Or that becomes
Any prediction, then it's positive. That's
Yes, correct. So usually we calculate, so we have model predictions, right? For all the model bounding boxes, we either calculate TP or FP. I think that's what you are coming,
yes,
right?
correct.
For all the ground truth, you either predict TP, I'm sorry about my drawing, TP or FN. For every model prediction, you check whether it is a TP or FP. If IOU is greater than 0.5 and if the class name is matching, it becomes TP, else it becomes FP.
Correct.
For every ground truth, if you have a prediction which has more than IOU more than 0.5 and the class name matches, then it becomes TP. Okay. If you have a ground truth, but you don't have a matching prediction, then that becomes a false negative. For
If there is an object in the bounding, it may not be apple, it may be arrow. The actual object is
then
false-
yeah, you are correct.
false positive.
So we had this car, right? And then we had this prediction. Sorry. So we have this is the ground truth. And then we had this is the prediction. Okay, then we had IOU of 0.8, but it predicted this as a bus. So this becomes false positive. And what does this become? This becomes false negative. You understand, right? If it makes one mistake, your false negative count also will go up and your false positive also will be count will also be incremented.
But there is another marks ground.
Huh?
False negative, your mark meter ground.
Yeah, for every ground truth, we have to account whether it is a TP or FN. For every prediction, we have to account whether it is a TP or FP. Finally, you will have this count, and this count. Your precision will be TP by TP plus FP. This is your precision. Your recall will be TP by TP plus FN. So your precision tells out of all the predictions, how many of them are actually correct. Your recall says out of all the actual objects, how many of them have been predicted correctly.
like the number of checks is being
Correctly predicted. So all these TPs are correctly predicted objects. These ones are the one that got missed out, completely missed by the model. These ones are the wrong predictions. False predictions, okay. Okay, that is another good question. That's where we are coming to. So you understood how precision and recall is calculated, right? So precision is TP by TP by F plus FP, sorry, and recall is TP divided by TP plus F1. Now, there's always a question, which one is more important? So it depends on the use case. For most of the industrial anomaly detection, industrial inspection use case, so the recall is important because they can't afford to miss any actual defect. So the recall should be very high. Okay, but you could actually have a very high recall and have a very low precision. Then what will be the impact if we have low precision? That's a. I mean, what exact specifically what is happening?
like predictions are there, but it's not correct.
What is the question for?
I mean, when I say low precision, what exactly is happening? I know model is not performing good, but
False positives are.
false positives are high. Okay, so what it means is that okay, a lot of the predictions are actually false, but I'm able to identify all my objects. Okay, in that process, I'm just trying to be a little careful and trying to make more and more predictions so that I'm identifying all the objects, but some of them are actually wrong.
But even if there is class mismatch, I mean, for precision score to be high, class should also match, right?
Yes, yes,
Otherwise, precision will be very low.
yes,
So if precision is high, that means my predictions are actually pretty good.
yes. So high precision, high recall is what an ideal situation.
Correct.
But in real world, trying to achieve a high precision, high recall is very challenging. In that case, you just have to only achieve any one thing. Okay. Then mostly people prefer high recall.
Correct.
Because you cannot afford to miss any defect.
You cannot afford to miss some prediction. Like
Any actual objects.
I think it depends on your application.
Yeah.
Most of them are.
So even in self-driving cars, there is like some pedestrians coming, right? There is actually only 3 pedestrians. Okay. But if the model is saying 6 pedestrians, that is okay. The car will anyway stop. But let's say if those predictions are not, it misses the pedestrians, and if it drives, then it will be very bad.
Recall is important.
Recall is what is more important.
It's very important.
Health domain also. Disease, right? If it is a cancer, let's say if you are having an automated AI model to identify the cancer, it's very tricky, but missing a cancerous diagnosis and the patient not getting treated is more dangerous than falsely predicting a person is having a cancer, right?
50% will be marked as 6%, and the 6% will be marked as this is what the person.
Correct. But making a healthy person as a disease is a false positive, but that is okay, or it's also not okay. But you can do some further screening, and yeah, that's why medical is very tricky to accept.
precision, I think precision should be high. But for driving, it doesn't depend if it's animal or person. I think it should predict something.
Predict something. Yes.
But because
It matters.
recall is say focus on recall only because if I taste my blood and report comes I am having diabetes, I can
He can take tablet, he won't die.
No, not tablet, I can start dieting. That will not ask me.
Ah, yeah,
But if it is telling you don't have diabetes, I'll give the same lifestyle, but it is bad for me.
Yeah.
But hospitals will like it anyways.
That answer.
Then like,
That's,
some tension, stress, they
Yes, yes.
Psychological issue.
psychological impact.
So you can go further. You can change further. But if report says I don't have diabetes, I will not go anywhere to test again. Yes, I am having.
Yeah.
Probably you can take second opinion. You might take 3 more tests and then take an average, something like that. But if you say no disease, then you are not going to test again.
Yes.
Right. Yes. No, no, no. For manufacturing also, recall is important, right? Because you cannot miss a defective product. You cannot send a defective product to your customer. If you have 100 products, okay, actually 2 only are defective, but your model is saying 5 are defective. Okay, which means that 5 will be taken it out and will be going through some manual inspections. And there they will identify, oh, okay, actually only 2 are defective. This 3 can be passed. That is basically high recall, low precision, because you do have a rework. That 3 false defect will be has to be manually checked and it has to be passed. But suppose imagine if you have a high precision and low recall, which means it will miss to identify that one of the 2 defect and it can go to the customer. Then it will lead to customer complaints. So there is a trade-off between customer complaints and rework. So low precision will lead to a lot of rework and extra processing time, but it will avoid the most critical customer complaints. So reaching a defective product a defective product reaching a customer is more critical than doing some recheck again and again. Like we introduce like a lot of
Testing decision values. Reinforcements.
I don't have to think that at once, but let's say you can take a similar like taking second opinion, right? You can also train multiple models. Okay, then you can take some sort of an average output. That's what you do in ensemble model, right? You know ensemble model in machine learning, right? So instead of just training one model, you train multiple models and take some OT. Then the chance of making mistakes becomes less, right? The same sort of an ensembling approach can be applied here. See, true negative is there. The entire background of an image is being actually true negative. So if you have one object here, all our those background, right, that becomes true negative. In object detection, the true negative count is too high. Okay, so then they don't take into account the true negative. Okay, so then okay, so we talked about the trade-off between precision and recall, which one is more important than that. But so as a data scientist, like you can also draw some, you know, sure. You can draw precision recall curve. They call it a spear curve. Okay. And you can calculate, so the graph will look something like this. Okay. So the higher the recall, the lower the precision, right? So let's say this is 0 and this is 1. If I want to get a recall of 0.9, close to 0.9, then my precision will become close to 0.1. If I want to get a high precision of 0.9, then my recall will become low. So this precision recall is always a trade-off. So that's why we plot this precision recall. So what we do is we calculate this precision recall in multiple confidence values. Okay, before that, what we need to understand is this precision recall is impacted by the confidence values. Okay, so the higher the confidence, higher is the precision. Okay, so this precision recall is impacted by the confidence value. So the higher the confidence, lower is the precision. Higher is the precision. Okay, and lower is the recall. Okay. Because what you're saying is I will only consider it as a correct prediction if it is very high confidence, which means it is more or less a correct predictions. But in that process, what you will also miss is some of the objects can also be not get detected. Okay. Yeah, I mean, you just keep only for sure it is correct. You are not taking any risk. That's why your precision will go high. So what we do typically is we calculate precision recall for every confidence value. So the confidence value will be calculated from 0.1 to 0.2 all the way up to 0.9. You follow, right? So you have a ground truth data, you have the model prediction data. Then what you do, you can set this confidence value in different ranges from 0.1, 0.2 up to 0.9. Then you calculate your precision recall values for each confidence values. Okay, which means then you take this table and then plot this curve, then you will get a curve something like this. So this will be 0.1, this will be 0.2, 0.3, all the way up to 0.9. Okay, you see, right? The higher the confidence, I'm getting higher precision. Lower the confidence, I'm getting higher recall. Okay, now these two situations are not suitable. I need to find a sweet spot. So I will select probably this is 0.4 is a sweet spot where I have a balanced precision and recall. Okay. So this is one of the important concepts to understand. What time is the lunch? 1 o'clock is the lunch break. Okay. Okay, so then we'll break for lunch and after that we'll look into the code. I think you will understand more better by looking into the code. Thank you.